The memory wall problem still exists and is considered to be an essential problem to solve. Aggressive prefetching can reduce the memory access latency, but it can also cause significant interference with demand memory stream, especially when multiple prefetchers operate in parallel. So, we need a prefetcher throttling scheme to make prefetching effective in CMPs. Most prefetchers, regardless of their logic, have two basic knobs: degree and distance. Degree determines the number of prefetch requests to issue per trigger, and distance decides how far ahead of the demand accesses the prefetch requests are issued. Degree and distance can balance the accuracy and coverage trade-off in prefetching. High-degree prefetching can potentially reduce the bits on the chip and thus enhance the system performance. Also, it may cause the caches to trash and consequently reduces the IPC. Hence, prefetching is a double-edged sword and needs to be controlled through a throttling scheme. Additionally, different applications are being run on top of general processors, and they exhibit different memory access patterns, ranging from sequential to indirect to irregular. Many prefetchers have been invented and adopted to deal with different access patterns and different requirements. Hence, the negative impact of prefetching can be exacerbated when different prefetchers need to operate at the same time. That being said, the question is, in the presence of many prefetchers and many cores and many knobs, what policy we should enable to throttle hardware prefetching. In this work, we take a new strategy to tackle this problem. We propose to design a prefetcher throttler as a reinforcement learning agent to automatically learn an optimal throttling policy via interaction with the rest of the system. The agent is the throttler that learns the throttling policy through trial and error. In the first step, we pick three simple features: accuracy, coverage, and access latency to determine the state of a system. And then, using a Q-learning algorithm with SARSA update, we find the best degree for each prefetcher. Experimental results taken from the Gen 5 simulator reveal that our scheme is robust and outperforms other approaches. As a next step, we will extend our strategy to many prefetcher scenarios using a deep Q-learning algorithm. In this design, we will use more features to represent a state through systematic feature selection, and also we consider more prefetchers to be more realistic. We aim to configure many prefetchers at runtime to better exploit their benefits. We also integrate Gen 5 and PyTorch to enable an infrastructure for exploring different training options and different CNNs. Finally, we will try to keep our design as simple as possible for real deployment.